So, all right, so my goal today is basically to not teach you anything, but to perhaps make you a little curious about language models. So I'll try to make things a little bit high level and simple, and in fact, I would love if you contribute to the talk by asking questions. The ideal talk would be if you talk more than I do, all right? So I'll try to say a few things to kind of like, inspire a few questions, but I would like to sort of like start with a bit of a riddle that I'll give this to ChatGPT. It's not gonna happen online or live, it's gonna, it happened already. But the only sort of like prerequisite is that you know what ChatGPT is. So who does not know what ChatGPT is? Everybody else is on board? Everybody has played with ChatGPT? Yes? All right, great, awesome. So can you help me solve this riddle? All right? Or tell me what this pattern is about. So I'll read the first example, 1 Dimitris, 2, a number written in English, Jonathan. And what's that last thing here? What is that last word in the first line of this example? That's where you talk. Yes? It's 3 written backwards. So I have a few examples where the first thing is it's a number, the second is a name, another number, another name. The names are written in different languages. There's Greek names, there's Korean names, written in both Greek and Korean and English. And there's also some typos because I wrote this example. So this riddle is not part of the training data of ChatGPT. In fact, because I'm not too smart, I made a typo here in 18, which was written backwards, but not quite right. So do you see what the pattern is here? Yes? Nice. Great. So minus 1.1, Steven, 3.2, a Korean name, X. What is X? 2.1, great. Backwards, yes, great. Yes, 1.2 should be the right answer. So do you think ChatGPT can solve this question? Let's have a raise of hands who thinks that ChatGPT cannot solve this. Okay. Raise of hands who thinks that ChatGPT can solve this. What about the rest who didn't raise their hands? Okay, so we'll make it a little more difficult. So this was like an older talk that I gave, and I used this example, but I'm like, let's just, the models are getting better, let's make it a little bit more difficult. I was making the slides, and I took a screenshot of the slides, and I gave the screenshot of the slide. So this is like a screenshot of my computer making the slides with the first slide that explains the riddle, and I'm asking ChatGPT to solve this. And ChatGPT basically does kind of like go through the examples and says that, there's like, backward letters and sort of like, names that play no role. And then the correct answer is 2.1. This fits with the format, kind of like how we saw before, but it didn't, it didn't do the 1.2. If this was a final exam, I would give 90% ChatGPT, right? So we should be generous. And hopefully this is mind-blowing. I mean, this still blows my mind when I see that. Like, how can a model like this do it? Like, if I were to show you this example 10 years ago, you'd be absolutely stunned. I mean, this is what you would call like intelligence or something like that. So how on earth are these capabilities, how do they emerge? And I would argue we don't even know how addition happens in these models. How do these models know how to add? And this is the work that I did with a bunch of amazing colleagues. If I say anything that you like, it's because of them. If I say anything that's silly and it doesn't sound right, it's because of me, and I apologize because of that. But let's kind of like dive a little bit into sort of like, the big chunk of this presentation. Are you, who's not familiar with language models? So a raise of hands who does not know what language models are. You won't need, okay, great. You won't need to know what language models are. I'll try to explain what it is. Let's say I create a sentence. My name is Dimitris and I'm an associate, kind of like missing word. What's the correct completion? Likely, I'm giving the talk, I'm talking about myself, I'm an associate professor. Likely, that's the most likely word. And the goal of a language model is to generate sentences that sound real, that sound kind of like typical. And it can be viewed as a conditional probability of like, what's the next most likely word given the words you've given so far. And how do we train them on like, a bunch of like, really long texts where you start with like, an uncalibrated model that has not been trained. Think of a baby that hasn't heard a single word. And you tell her, the sun was shining, complete the next word. What will the 1-year-old baby say? Something random. That's what an uncalibrated model would do as well. And you train it. You say, well, this is not the right thing. The right thing is to say, the sun was shining brightly, blah, 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 blah. So you train the model on all the prefixes of your training data, okay? So the goal here is to basically build this probability. When you penalize the model and say, well, this is the correct word, you said the wrong thing, calibrate your weights in a way that corrects the mistake that you made. And this is what we would call the cross-entropy loss, roughly speaking. So you don't have to know what it is, but that's kind of like roughly speaking what's happening, or how we train the network. And this was what maybe vanilla NLP was doing back in the day. And not a lot of interesting things happen, I kind of want to say, before they train on really large data sets. So I want to take a little pause here and see if everybody's on board with kind of like how we train these models. You don't have to know what it is. You don't have to kind of like understand architectures and algorithms, just a high-level idea. Any questions? We're good? All right. So the other thing is the model doesn't know words. It just sees integers. So there's something called tokens. If you use like OpenAI's tokenizer, you map words to tokens. Depending on different languages, you get different tokens, but the model does not know words, doesn't know characters, just a bunch of numbers, all right? It's kind of crazy. If you go back to the riddle example, this is just a bunch of integers, like it's just viewing the matrix or whatever, and the model's coming up with great stuff. So interesting things happen when you train on the entire internet, and this is what this paper did. So are people familiar with the GPT architecture? Is basically what is powering ChatGPT, and there was a paper, Language Models as Few Shot Learners by OpenAI in 2019 or 18. And they trained the language model on basically everything that was available to humankind, all right? So like the internet, think of like all the text in the internet, all the good stuff, all the bad stuff, whatever, just trained a really large model to predict the next most likely word. That was the goal. And the goal, or sort of like the premise of this paper is not, we trained a large model in like, a bunch of data, but that the model does special stuff. It does a thing called in-context learning. So the idea of in-context learning is that the model is not trained to do a bunch of things like addition and translation and fixing typos, but if you were to prompt it, if you were to kind of like coerce the model to be in the mode of solving something, it would solve that thing. For example, you would give examples of A plus B equals C addition, and it would add and enunciate an example. It would do fixing typos, translating from like French to English and whatnot. So that's the idea of in-context learning, a really big generalist model that if you prompt it appropriately with the task that you have at hand, it's going to solve that task, okay? That was the premise of this paper. We went from models that were like, okay, just translation models or fixing typos to like this gigantic mammoth of a model that could do all those things. And the way that sort of like, they manifested that is by, having a bunch of different tests and looking how the test accuracy across all those weird generalist tests looks like as you vary the number of, like how big the model is. So this number here is like how big the model is in terms of number of parameters. How many tuning knobs do you need to like basically define that model? And they used up to 175 billion parameters. That's a lot of parameters. And they saw that basically this in-context learning capability ignore everything apart from the trend that goes up as you increase the number of parameters. So that's what they saw. And the idea, again, is that basically LLMs trained on vast amounts of data acquire skills like translation, arithmetic, algorithmic reasoning, and whatnot. And why is this useful? Because you have like one big model. You don't have to train a bunch of models. You have like one really large model that can do everything for you, all right? And the only thing that you have to do is basically prompt it. So what does prompt mean? Just talk to the model. Just talk to the model and say things in the right way, and the model likely or hopefully is going to do it, all right? Why is this surprising? Nobody told the model to do these things. It just learned it from this sort of like unstructured, unsupervised type of training that it has kind of like undergone. I'll take a 5-second pause for questions now. How do we feel about these things? Any questions, thoughts, or anything else? All right, so how do these skills emerge? Well, basically, there's been a lot of papers trying to understand, like, how does the model learn arithmetic? How does it learn, like, translation and whatnot? And it's sort of like, we don't really know, but I want to focus on arithmetic, not because, like, an addition in particular, not because addition is somehow important. I guess it is important, but, like, it's just like a simple skill, but it's easy to run ablation studies for it and really fun to think about, and whether, like, the way that these models are trained is kind of like the right thing for arithmetic. So how does the training data looks like? Look for examples of addition on the internet. You have a bunch of like, examples where, the steps are broken down into pieces, or on Wikipedia there's like, addition charts and whatnot. But it's very sort of like messy and unstructured, right? So how does addition emerge when you train on data like that? And how do you even approach this? Like, what do we even do to what's the right hypothesis to pose? What's the right experiment to run? And people have thought about this, but it's kind of like problematic. There's too much data on the internet. The models that these people trained is for what we would call the GPU reach. You need a lot of GPUs to train these really large models. And our solution is basically to kind of ablate. So we'll train a really baby model, the baby sort of sibling of ChatGPT, and we'll call this NanoGPT. All right. So let's see how a model like NanoGPT learns addition. This is a very tiny model. And in the next few slides, you'll see me go into just a rabbit hole of addition, right? So if you were to tell me 10 years ago, I would be just studying how to add numbers, I would probably laugh at you, but we'll just maybe learn a few interesting things. So here's how I'm going to train my model. I'm only going to have very simple vocabulary, just the numbers, all right? So the tokens will be integers, which will represent the numbers. For now, let's focus on addition, in spite of the fact that we trained on multiplication and other stuff there. And let's start with training on A plus B equals C examples. This is the standard addition examples, 2-digit examples, randomly sampled from all possible pairs of 2-digit examples. And the way that I train, so think of it as a huge text file with just A plus B equals C, all right? How do I train? For every token I have, or for every prefix of that text file, I try to generate the next whatever token, and if the model makes a mistake, I penalize it and say, well, you did the wrong thing, calibrate your weights. And do this many, many times for your entire data set. For most of these steps, these generations are kind of useless. Like, why would the model generate the plus sign after 0? There's no particular reason. But once in a while, it's kind of like a useful bit or a useful token that the model has to generate, and from that, it probably learns something. Will the model learn? Let's see. So that was the first question we asked. So if I train on only this type of example, so this is a nano baby GPT, we only train on text files of A plus B equals C. Will addition emerge as whatever the skill of this model? Here's what we see. Well, things are not very good because you go up to 80% accuracy or 90% accuracy after seeing, 10,000 examples of addition. And that's a lot of examples, right? And the model still doesn't quite capture even for that fixed length, just 2-digit examples, it's still not sure how to do it. And then we start thinking about it. So I'm going to ask you a question now. So let's say I ask you to add, I'm not going to ask you to add numbers, but let's say I did, right? Let's go back to elementary school. Let's say I asked you to add 1,343, 7,899. How would you do it? How would you add two numbers? I know it sounds like a silly question, but it's gonna get us somewhere. Probably, you'll start with what digit? The least significant one, right? So you'd stack the numbers one under the other, and then you'd start with, let's call the resultant, say, BCD. You'll start with computing D, right? Now, when you use a next token predictor, like you give a prefix and you say predict the next word, the model is forced to work in the opposite way. The model is forced to spit out the most significant bit first. Now, I don't know about you, but if you were to ask me to add these numbers, and in the absence of a scratch pad, tell you what the MSB is, it would take me a long time, and I would probably be wrong. The reason behind that is because trying to output the MSB first is a harder function to learn somehow, all right? So the idea here is the following. So we'll do something weird now. So we have the standard format, the A plus B equals C, in which case, if we want the model to learn how to add, it sort of needs to look at every single digit and output the MSB and internally sort of implement the entire algorithm of addition. However, if I train the model in the reverse format, a format that doesn't really exist but we'll make it up, where I flip the digits of C, the resultant, the only thing that the model has to pay attention to is kind of just two digits and sort of what the carry was of the previous addition, right? So in terms of difficulty, the second one is much easier to learn. Now, where am I going with this? Well, what if we trained, so I'll change the training form. I'm not going to train on A plus B's now, equals C. Huge text file with the only difference that the resultant C is going to be flipped. All right, so I'm just going to flip the digits of the resultant. And here's what will happen. So on the x-axis, sorry, this is the x-axis. The x-axis is the number of training examples. The y-axis is the accuracy. And what do we observe? Well, so the yellow is reverse, plain is the blue one or black here. So we see that the reverse gets to 100% faster. Still quite a few examples, like 5,000 examples. I think you'd probably learn addition with like much fewer examples, but it learns 3-digit addition, okay? Now what did I just change the format of the data, right? But like this kind of like does something magic for the model. It just makes things easier. So what I want to talk a little bit about is how the data controls the quality of your training cycles, how easy it is for the model to learn stuff, all right? Quick pause here just to see if we're all on the same page and if you have questions. Yes? It is, yes. So the way to answer this question is that it is, the model has the capacity to do it. So yeah, the answer is yes. Great. Any other question? Yes. Yeah, so I have two training data sets, separate. Think of them as big text files. The first one has examples that look like A plus B equals C, right? And C is always the correct result. Here it's the same thing with the only difference that I just like reverse the output. So instead of having the MSB first, like the result of this at A plus B is like 495, I just like flip things around. So the last becomes the first, the second to last becomes the second, and so on and so forth. And all of my text file, all of my training data look exactly like that. Make sense? Good. Yes? So in these cases, so all right, so there's basically 100 times 100. How much is that? That's a little less than that, right? So, and we actually do test that the number or like the specific test examples are not part of the training data. But at some point, you're right that there will be overfitting. Like if you just keep increasing the number of examples, you basically run out of examples to test. It's a very good observation. There's another, yes?
If the model has the capacity to achieve 100% accuracy using the reverse format,
yes.
why doesn't it achieve 100% using the blend format?
Right, so this is a great question. It's hard to answer it in a way that's like, mathematically correct, but I'll try to give a sort of like, a high-level idea. Because of the fact that the model needs to pay attention to everything in the normal format, as you increase the number of digits, then the effective size of the model that you need to do this addition increases as well. Does that make sense? Because internally, you have to kind of like build something that like keeps track of all of the n digits. So that thing to exist has, it requires from the model to also increase as a function of the number of digits. In the simple format, that's not the case anymore. The only thing you need to keep track is like just a carry and two integers. Yeah. Great. All right. Awesome. So does internet data, if you were to look on the internet, are these the examples you'd find? Probably not. The examples kind of look like this, right? So we have, you add like, I don't know, this number with this number, and then you kind of like have step one, start with the digits in the ones column, step two, blah, blah. So this is kind of like a step-by-step process of learning stuff. In fact, so let's say you had, again, maybe a 5-year-old that, they've never seen addition in their life, and then you say, well, I'm going to give you examples, right? So you give the 5-year-old examples that look like, I don't know, like 3 digits plus 3 digits, and whatever result. But you say nothing about how the output is generated, and just keep giving them examples, and then you hope that maybe they will learn. They will never learn, right? So it's going to be really hard to explain or to learn things without intermediate steps. But if you give a child this, and maybe a few examples of what's the algorithm, like what do you have to do to add? It's kind of like just a local thing that you apply to every single digit again and again. And if you kind of have a grasp of what that sort of simple operation is, you're kind of done with knowing or understanding what the additional algorithm performs to the numbers. What if we do the same for the language model? So let's treat it like a child and kind of just make things really easy for it. So I'm going to give the training data now is going to be basically data where we go in reverse order and we produce intermediate carries and we take it step by step. This in the literature has a name. It's called chain of thought. So you basically, it's kind of like the chain of the thought process that you use to generate these digits. And so I'm going to train on basically two things. We call it a scratchpad. So now my text file is a bunch of examples that look like that. What I mean is that you have a bunch of intermediate steps. You can make it a little bit more, intense, have like a lot of, if you will, sort of details about, what is happening, how many digits are left after every spot and whatnot. And I'm going to train on that kind of data. So there's no A plus B equals C examples. There's no reverse. It's just like only this format of data. And there's no pre-training in my model. I start from like random models that are completely unable to do anything else before we train them. And so here's what happens. So what I'm going to show you now is the test accuracy curve for all these formats. And something really cool happens here. So basically, the green and the red curve are the accuracies for the chain of thought data. All right? So now you train with all the intermediate explanations, and something magic happens. There's sort of like almost a phase transition where the model goes from like not knowing addition to sort of like, grasping it fully, at least for the 2 or 3 digit lengths that we're testing them here. And perhaps the main finding at this point is that somehow the data format, and if you will, the quality of the data and how much they explain what's going on, has a dramatic impact on the ability of the model to learn things. In this case, arithmetic or just addition, right? So I want to touch a bit on like, a few things, like why is chain of thought easier for the model? So there's a mathematical, if you will, grounding to this. And also I want to talk about something that we call length generalization. Basically, does nano GPT or even GPT understand what it means how to add numbers? Before I go there, I'm going to take another pause to see if things make sense. So again, the main high-level idea here is that if you make things really simple for the model will learn faster. Okay? Any questions? Yes?
Have you tried using randomly building scratchpads just to give more capacity?
Yeah, it's a great question. This helps the model length generalize more. So basically, there is something that happens with these models that basically they will overfit to the template of the data. And by messing around with things, by hiding things from the model will basically sort of like start doing some infilling that will allow it to do a little bit better in out of distribution type of scenario. So it helps a lot if you do that. Yeah, it's a good question. Great. Any other questions? All right, awesome. Yes? Of training the model? Let's say that it doesn't, like this should happen in any language, but this is with PyTorch, yeah, in Python, yeah. Okay, so why does chain of thought data make it easier to learn? So the idea here is that basically COT involves longer examples, but every single token somehow matters in the sense that the model will learn, smaller or easier, like a longer set of easier functions somehow. So we have a paper that we kind of like explain this, but somehow the idea is that instead of like, if you were to do the A plus B equals C example thing, and sorry, this is like really dark probably to see what it is, but if I were to just ask you to learn A plus B equals C without any intermediate steps, you would have to internalize a really hard function. And you have to kind of like, run the whole algorithm in your head without outputting any results. If I were to try to teach you addition by showing you everything else in between, the footprint of the calculation is really high dimensional. There's a lot of tokens involved. But the individual functions, kind of like know how to generate each one of those tokens, is much, much simpler. And in fact, there's a lot of repetition as well. Every step is basically kind of like the same. So that's a good thing. And that's a high-level idea of why chain of thought data kind of like helps these models learn. There's a few sort of like things with regards to like, well, maybe chain of thought data is like really long, right? So is it like efficient? So if I were to count wall clock time, training the model to like reach 100% accuracy, is chain of thought token efficient? Is it like cheap to train on this data? Because as you increase the explanations, the stuff that the model is trained on just increases proportional to the size of the explanation as well. And what we basically find, so we kind of like summarize in this figure, which is like the test accuracy as a function of like, how many tokens the model has seen during the training data. Chain of thought data is a good idea. The model, in spite of the fact that the model has to see more things per example, it needs significantly fewer examples to learn the right thing. I'm going to skip this slide. And so we spend a lot of time kind of like thinking about this. The paper has a lot of stuff beyond addition, with regards to subtraction, multiplication. What happens if you train on like, I don't know, like Shakespeare, in combination with the arithmetic data? What's the effect of mistakes and noise in the prompts and whatnot? I invite you to check out the paper. We really enjoyed writing it. It's a lot of fun to think about these problems. But I want to kind of like go back a little bit and think about generalization. So generalization is the ability of the model to do stuff well outside of the range of training data it's in, right? So when you're tested on multiplication, it's probably a number that you've never seen during learning multiplication or addition. And we kind of want to know if the model also has this capacity to generalize, basically do the right thing outside its training data. And also, I'm really curious about like this phase transition, like the 0 to 100% rapid transition of like understanding addition or like knowing how to do addition, at least in this 2 or 3 digit example. And there's something kind of cute here. So why does addition emerge rapidly at a relatively small number of examples? Let's think about this. So this is an addition chart. This is like a matrix or a table. Every single column here is indexed by the integer you want to add, and every single row here is indexed by the second integer you want to add. So whatever, 3 plus 2 is 5. And what is the rank of this matrix? So how many, like if I wanted to describe this entire matrix to you, how many numbers do I need to describe this matrix to you? So the rank of this matrix is just 2, right? So basically, I only need effectively 2 vectors to describe it, all right? And there is theory from sort of like low-dimensional kind of like research from compressed sensing and matrix completion that says you can learn these easily describable matrices. So the addition table for any, up to any digit that you like is always easy to describe somehow, all right? And that kind of like, easy to describe property makes learning easy in terms of like number of examples. And we do know that when we try to like, recover matrices, so what the model is doing is basically, we start from no examples, so like all the, A plus B's are hidden. And then I start revealing a few things. The model doesn't know what's happening, and then at some point, it knows the whole matrix. And this happens rapidly and early in training precisely because learning a fixed addition chart is low rank, okay? Now, low rankness doesn't really kind of like this viewpoint does not really explain a lot of the magic stuff that happen in NanoGPT. So like for traditional matrix completion algorithms, if I were to hide a number, you wouldn't know how to add with that particular number. In spite of the fact that sometimes we may train NanoGPT without ever seeing, let's say, I don't know, a particular integer, the model still knows how to add. So I'm not going to go into details, but the whole point I'm trying to drive here is that there is some inductive bias in the model that actually does learn things outside of what a simple matrix completion kind of like, mental framework would allow. Let me go kind of like on sort of like a last step of this journey. So the past few slides are basically trying to explain why the sharp transition happens. So the sharp transition, again, is sort of like predicted, if you will, by some matrix completion theory. But I think the right thing to ask is, does NanoGPT know how to add? So let me ask, what does it mean to know how to add numbers? So this is a very, hotly debated topic on Twitter as well. Do these models know things, or are they, just like parroting stuff from their training data? So what would be like a very generous, if you will, definition of like knowing how to add? What does it mean, know how to add? Any thoughts? Yes.
Maybe know the root.
Yes. Knowing the rules. So maybe if we abstract a little bit, just knowing, like, at the very least, the algorithm, if you will. Right? So what's the algorithm of addition? If I were to give you 2 numbers, like what are kind of like the mechanics that go to add these 2 numbers? So let's move on with this very simple definition of like, do these models basically perform addition correctly, especially with regards to out of distribution stuff. So here's what I mean by that. So I'll train now this model with a very particular training data set. I will include 1-digit examples, 2-digit examples, and 1-digit examples and 3-digit examples, but not 2-digit and 4-digit examples, okay? So I'm kind of like skipping a few digits. So if you were to teach somebody 3-digit addition, they probably know very well how to do 2-digit addition. These models actually fail in length generalizing both backwards, like smaller digits that it hasn't seen during the training data, but also forward. Like it doesn't, like even if you train the model on like 100-digit addition and you skip 5-digit addition, the model does not know how to add 5-digit numbers. It's kind of crazy, right? Yes?
So I will repeat it
Yeah.
once more. Can you generalize the input, the length of the input in the LLM and still get the same model? I mean, since there is variable length and it learns to do only an addition with, let's say, 3 digits, you can't apply the same weights, let's say, for the model to a 4-digit application or a 2-digit application.
That's a great question. So maybe the way to think about this is that somehow, if you were to magically teach the model like a local rule that just applies to 2 digits, perhaps there should be a way for that model to learn how to add beyond that by just applying this kind of like local rule. Am I getting the question right? Is it sort of where you're going?
Yeah, it's a question of you have, for example, 1,000 weights in your neural network, and when you do this with 4 digits instead of 2, you have 1,500, let's say.
Yes.
It's how can you do this transition and expect to have similar results?
Okay, so that's a good point. So a big failure of these models happens precisely because of positional information. That for them, the digit 2 at position 1 is different than the digit 2 at position 5. And if it has not seen things at position 5, it just does not know how to do things at position 5. So that's kind of like pretty critical, and especially in the recent research of trying to understand this failure case of like, why do these models don't know, why are they seem incapable of like learning this. And the thing is, like, even if you try GPT-4, it fails at like, 200, like it knows how to do like up to 250. You try 255. I mean, of course, why would you use like a 1 trillion parameter model to add numbers? But whatever. Let's, in spite of that, of the perhaps not very meaningful kind of like addition thing to ask these models. But if you do this, you will see that these models at some point fail, even the really large ones. So even the most capable models, the ones that are kind of like converging to AGI or whatever you want to call it, they don't know how to add. They can describe the algorithm of addition, but if you ask them to add, they can't add. It's pretty interesting.
So for them, if I understood correctly, it's mostly a matter of topology of the numbers.
I don't know if the right words. There is some topology going on internally in the model in how it maps things to like embeddings, and that is broken in some way.
Okay,
yeah.
Thank you.
So I think a valid criticism of this figure is I only trained up to like, just like, 3-digit examples. But if we tried this example up to, whatever, 10 digits and whatnot. And we're like, let's see what happens if you kind of like try to train for like 1, 2, 3, 5, 6, 7-digit examples. So we skip 4-digit examples and we skip 8-digit examples. Does the model learn, does it learn how to do the addition algorithm internally for the digits it hasn't seen? And again, sort of like surprisingly, even in spite of the fact that the model knows how to do 7-digit addition, completely fails to do 4-digit addition. And what this figure show here, these slides are super busy, probably can't see what's happening. In fact, you can completely ignore what's happening. It's not a problem. But maybe what I want to say is like, during training, the model at some point learns how to add 4-digit numbers and then forgets. So if you overtrain the model, somehow overfits to the template of the training data, and it says, well, this is not what happens exactly, but perhaps a hypothesis of like, well, if the only things I've seen are not 4-digit examples, why waste capacity in learning how to add 4-digit examples? And so we kind of like try to examine, if you will, this hypothesis a little bit. And by that, what I mean is that we try to figure out like what's happened, like what are the what is happening during a failure case. Again, tiny fonts here, sort of like you can ignore this slide if you will, just listen to my voice. But the idea is that somehow the model tries to do for the 4-digit example what it would do for the 5-digit examples. It just comes up with like a 5th digit because that's what it saw in the training data. It didn't see any 4-digit examples in the training data. So kind of like the high level idea is that, and sort of like answering the question, do these models know addition? They don't really kind of like, they don't learn these algorithms. They learn shortcuts to those algorithms. And you can think of this as like just pseudo algorithms. And The reason why this happens is maybe a little bit complicated, because addition is a very simple algorithm, right? Just like a simple local rule. And you can ask, maybe the model does not have the capacity to implement this algorithm. The answer to that question is that's not basically true. So, we have work that basically shows you can implement a full-blown reduced instruction computer with sort of like a finite layer transformer. So there's nothing wrong with the architecture, if you will, like it can implement whatever you like. And the problem somehow lies, if you will, in the way that the model attempts to understand what a number means. So again, for a model that's sort of like, trained in the way that I explained, there is something called positional embeddings. So what positional embeddings are, think of it as indices. Kind of like, have to tell the model what's the first token, what's the second token, what's the last token. And these indices really mess up the ability of the model to learn stuff, because again, number 1 at position 5 is a different, it's mapped to a different vector than number 1 at position 10, right? So the model has to learn a very complicated thing, or a map, if it has to learn addition properly. So the idea somehow, again, or the explanation of the failure is that there is sort of extreme simplicity bias. The training algorithm is lazy and likes simple stuff, right? So it will not waste capacity. The model will not waste capacity to learn something that is not within what its implicit bias sort of like, dictates, right? So there's some implicit bias, there's some bias in the model and the training algorithm that kind of like, if you will, coerces the model to learn something. And the way that we set up things, the model would just not waste capacity to learn lengths that it has not seen during the training. So there's been a ton of work sort of, both before our work and then inspired from our work on kind of just trying to understand and attempt at fixing length generalization. And the overwhelming explanation of why this happens is sort of like this, if you will, kind of like this idea of using particular indices for every token is kind of like the crux of the issue. And the way to fix this is currently really hacky, if you will. So let's say I want, again, to train a model to just add numbers. The way to do this is like use really weird indices inside the architecture, but also like specify with explicit indices when I give examples what whatever is a digit is. And even if you train, there's been a lot of, let's say there's like, 20 papers on this trying to fix this. And even if you apply kind of like, every single trick in the book, still if you try to train a model with a limited size of training data, at some point it will break when it tries to add a very large digit number. So what's the point of all this? So the point of all this is that, maybe, so there's something called the bitter lesson. I don't know if you're familiar with this. So the bitter lesson is that maybe we shouldn't think about like, over-engineering solutions for like, teaching skills to these models. And perhaps scale will be a remedy for these issues. What does scale mean? Use the biggest model possible with the maximum number of GPUs that you have available on every single data point you can generate. And perhaps at some point of scale, the model will just do the right thing, okay? And this bitter lesson is sort of like a popular, if you will, rule of thumb, because it has been sort of verified many times in the past. And maybe we shouldn't worry about these models not doing the right thing right now. Maybe at some point they will do the right thing. And in spite of GPT-4 failing at some point, it can still add 200-digit numbers. Right? So maybe if you train on like, more data, you generate more internet data, maybe it can add like 300-digit numbers or whatever. But I think the lessons that we at least learned from doing sort of this study on arithmetic is that, first of all, it's kind of like valuable to think about the way that these models are trained and the way that you set these models up for failure. So the next token prediction is in fact suboptimal for teaching skills to these models beyond even arithmetic for many sort of like algorithmic reasoning skills. The data formatting matters a lot. It sort of like really controls how difficult you make the life for the model to learn things, right? So again, think of the example of like teaching to a child addition with like only A plus B equals C examples without any intermediate steps and without allowing that person to like use a scratchpad. That's a really hard thing to learn. However, you could use what we call the chain of thought data that kind of like describes in fine detail every single thing you want the model to learn. And that makes things much easier. And there's this whole cool sort of emergence, the idea of emergent properties. In spite of the fact that these models are not trained for a particular task in mind, they learn things. And like understanding why this happens is still a big open question, and we've been thinking quite a lot about it. And the other thing that I think is really cool, and we've been trying to think a lot about, is this idea of length generalization. How do we teach algorithms to language models? Because at the end of the day, what happens with this, what happens with ChatGPT is like when you prompt it to do something, in its internal knowledge base or whatever, it sort of like picks up an approximation of a composition of approximation of algorithms it has learned during training, and through that composition it tries to output the right thing for you, depending on the question that you ask. So I would like to have just a concluding slide. So the first thing is that language models are a lot of fun. So I've been in Madison for 8 years. For the first 6 years, I've been doing large-scale machine learning, but more on just distributed training algorithms. How do we make things faster? And when I got tenure, so when I monopathic, I'm not sure what the right word is in English. I just felt a little bit bored about the stuff I did, and I'm like, I'll just start making things. And this timeline sort of left with OpenAI and specifically free on late run, and I started training and solve weird riddles like the one I saw before. And I'm like, there's something here. There's something really cool about these models. And we understand almost nothing about the ability to follow instructions, implement, even if these are pseudo algorithms, it's really cool that these models can do it. And for me, I'm trying to understand, like, what is the right way to do it in terms of the data, in terms of the models, and whatnot. So I will kind of like end here with a few questions that we've been thinking about. And I hope that you at the very least are a little bit curious about sort of like the magic of ChatGPT and how can it do the things that it can do. So I'll stop here and I'll be happy to discuss more with you.
Hi. Hi. Very nice presentation. So I have a question based on what you said about the extreme simplicity bias. Yeah. I was wondering if this is something that holds true, then why don't we inject all the formal rules like in an explicit way so that the model is able then to indeed have the extreme simplicity bias injected already?
Yeah.
And if that's, the question goes to the fact that these models are very capable on instruction following, and I wonder whether we should also focus on how to build these kind of instructions in the more structured way.
That's a great question. So perhaps the way that I interpret this, maybe this line of thought is that if you want to teach a model, I don't know, an algorithm, and that algorithm is just a composition of like some logic rules or some just like local steps or whatever, you could perhaps like teach those individual steps, and then at some point these steps could be perhaps composed in the correct way to output the correct result. So we tried, people have, including Michael, we tried to do this quite a lot, and still the models just don't do the right thing after a while. So like after a while, by that I mean like, there is certain, so what you're onto is like definitely an ingredient for length generalization, but it just does not seem to be the only ingredient. This is just not enough for the model to do kind of like the right thing. Larger models, like real, language models like GPT and whatnot, GPT-4 and whatnot, they do seem to have the ability to implement algorithms by sort of like spelling out the steps if you sort of like ask them to do it, and that seems to like increase their capacity for length generalization. But I'm not certain with regards to the limits of that length generalization capacity. But again, very good observation. That's certainly an ingredient for moving forward.
Thanks.
Another one is simply
substitute the variables with the digits and actually implement it, as opposed to just working from next token prediction of the actual data.
Yep.
So is it that there's so much more data, like so much more instances of addition that it kind of forgets the algorithm? Like, is there some understanding of why this happens?
That is a phenomenal question that has been torturing me for a year, and I don't have a good answer to it. I think, so here's what I think will happen. I think what will happen is because of these models, they will be just trained on larger and larger data sets. Maybe we won't care if they won't be able to add 10,000 digit numbers because we will never have to use sort of like that ability. But going back to the core of the question is like, why, it's in the algorithm, like what is it in the model itself or the training process that does not allow the model to like do the right thing? I don't know. I really don't know. And it's been bothering me for quite a long time now. I think there's kind of like two approaches to like, at least in this literature, to think of this problem, like whether this is a deficit of the architecture or whether we can say, forget about changing anything because like it works great for many things. And maybe it doesn't matter to fix addition, but like if you wanted to fix addition, maybe you can just think hard about like, what's the right kind of training data, right? Could the answer be provided by just like having a magic sort of like template and set of data that you train on? Or do we need to actually perform some kind of like surgery in the architecture? And it may be the case that we may be missing something about the architecture that's not quite there. At least this is what recent papers are pointing to, which is all the fixes that were somehow suggested. They, both consider what's the right format for training data, but also what is that one little thing I can change about the model architecture that will allow the model to do the right thing, at least for many more, for larger lengths than the ones that it's been trained on. So just spilled my oranges. But yeah, that's how frustrated I am that this thing is not working. So yeah, it's not an answer. I'm sorry it's not an answer, but we've been thinking about it really hard. Yeah.
Hi again. Did you or has anyone else perhaps tried visualizing the learning process, like up to 3 or 4 digits? I imagine you could make a grid, like 1 pixel is whether the model got that combination of numbers right, like the plot you showed, and maybe get some insight this way of how the model learns, maybe even correlate that with the sample that you used for that step or all the previous samples?
Yeah, that's a great question. So basically, maybe if I were to rephrase this, is like, what if we were to perform some diagnostics, if you will, both in terms of like, ablating for the data that we use, but also what if we looked inside the model? Like we looked at the representations it learned, the way it learned how to map numbers to vectors and whatnot. What would that tell us? And so this is a tangentially related field, something called mechanistic interpretability, just kind of understanding on a mechanistic level what's happening internally in the model. So that approach has helped a few of those papers figure out why do those failure cases happen. So for example, if we were to look at the A plus B equals C a training data, and you look at the attention patterns inside the model, like somehow where is the model looking at when it's trying to output a digit? It's looking at everything, every single digit all the time for every single token generation. So that kind of like, gave us the idea that like the model is learning something really complicated. Addition is much simpler at like, beyond just like looking at everything. You can just look at 2 digits at every time and kind of like, perform the right thing. And so that kind of like inspired us to some degree to like, look at that reverse format. And, this maybe the way to answer your question is that this sort of like, reverse engineering what's happening internally can help quite a lot in figuring out how to move forward on this question.
Okay, thank you.
Yeah.
Any other questions?
Sorry, is there anyone else? Okay. I'm here. Hello.
Oh, sorry.
So thanks for the presentation. It was wonderful. I missed the point. Why would you prefer to take this path and not use function calling for the addition problem?
That's a great question. So why do we care about addition? I would argue addition is not important precisely because you could use a calculator, and these models can be trained to use calculators and Python interpreters and whatever. But my sort of like what has been bugging me for a long time is that, I mean, we do think that these models are sort of like composing internally algorithms. So if I were to like, I just, in terms of like scientific inquiry, I'm just like not satisfied with the answers I've seen so far. And like, why are these models doing what they're doing, how they're learning it, and why can't they do more than they currently do? And so arithmetic and addition is just a very easy to test bed. So
it's not about solving the problem.
It's not about solving, the addition. Yeah.
I only came at the end of your talk, but I know of your work, and I have a question about these language models, whether stochasticity and probabilistic elements are something that people are interested in embedding in these models. And apologies if you already addressed that.
No, I haven't. It's a great question. So basically, perhaps maybe a way to reframe this is that, is there any maybe element of randomness that could be used in these models to make things better in terms of performance? So there's two ways that randomness could help. So one way is that if you somehow generate data and you inject a lot of randomness in the data by like including noise and whatnot, that is helpful with regards to like the models start breaking their simplicity bias, if you will. The other way where randomness is really useful is, at the parameter called temperature. So when a model is picking a token to generate, kind of like output, it does so on advice from a probability distribution that has been internally built. And the way that the model is sampling a token is basically by kind of like looking at the maximum, if you will, probability and just picking that. Instead of that, you could say, well, what if I just sampled according to that probability distribution and see what happens? And so these sort of like, adding that extra probability, if you will, aspect at the end of the model when it generates can in fact help the model escape weird, if you will, kind of, I don't want to call them minima, but sort of like weird dead ends somehow. People have been looking at it quite a lot, but I don't think there's a satisfying answer to that either. Yeah, that's why it's a great field. There's a lot of open questions.
Thank you.
Yeah.
Any other questions?
Related to temperature and decoding. So if you try multiple times, does it get it right at least some of the time? So if you do things like consistency checking, chain of thought multiple times.
That's a great question. So basically, here's one thing we tried. So we tried instead of sort of like single token, if you will, prediction, you can do something like a block, almost like a block maximum likelihood, if you will, prediction, where instead of like, outputting the maximum probability element at every step, you just look at the whole list, if you will. So I don't know if you're familiar with like list decoding, but something like, what if I were to output the top 10 output in terms of like just aggregate probability? Even if you sort of like do that, computationally really generous sort of gift to the model, it still is not able to. It improves a little bit, but it's not like somehow the correct answer is not hidden in that high probability tree that is generated. So it seems to me that currently just playing with the decoding algorithm is not going to be just the single silver bullet that will solve this, but it likely may be part of the answer eventually. Yeah.
Also, have you tried replacing digits by words? Does this make any difference?
Yeah, that's a great question. Yeah, we did try with words as well. So just like write everything numerically. Essentially what this changes is that the number of tokens that are used to represent a particular digit. It did not help, unfortunately. Yeah, so it didn't really do much. Yeah. Awesome, great. Well, thank you for being a fantastic audience. I will be hanging around for a little bit. Come chat.